Okay, good afternoon. We're going to pick up right where we left off on Friday, talking about some basic complexity theory. I had already sort of focused us in on a general notion of some kind of Turing machine or equivalent model, and focused us in on decision problems. Where your goal is to accept or reject an input, which just simplifies the conversation to be talking about binary inputs. If you're thinking about an optimization problem, you can turn it into a decision problem by setting a threshold and asking if the optimum is above or below it. If you have a decision tool, you can turn it into an optimizer by doing some kind of binary search for the optimum value. So this is really just a simplification for discussion purposes. We talked about languages. A language is just a set of inputs that is supposed to be accepted. So we say that we have a machine for a language, or a machine that accepts a language if it accepts precisely the inputs that are in that set. And then we can start talking about classes of languages that can be accepted by certain kinds of machines, right? And so P, the complexity class we're most familiar with, is languages that you can accept or reject in time, which is polynomial in the input size, right? But then we started getting into weirder classes where there's this general notion of being able to provide some kind of advice string in addition to the input. And the idea is that the machine is looking at the input, but it is also allowed to look at this advice string. And so the class NP, for example, is languages that you accept that are accepted by non-deterministic polytime machines. And what does this non-determinism mean? Well, if a given input is not in the language, if it's not supposed to be accepted, then no advice causes the machine or the algorithm to accept. However, if it is in the language, then some advice string, the machine to accept. Okay, and often this advice is in the form of, here is the answer to the question. Now, if the advice is giving you the answer to the question, what does the machine have to do? Why is it even meaningful to talk about accepting with advice if you can just provide the answer in the advice? Right, the advice could just be, the answer is yes, output yes. Yeah? Exactly, right? If you wrote a machine that just followed the advice, then essentially every input would be accepted because it follows the advice that says accept the input, right? So it's still the job of the machine to check that the advice is good and that the answer that the advice contains is actually a correct answer. And so just saying that the answer is yes is usually not sufficient, right? because it may be computationally intractable for the machine in polynomial time to actually check whether the answer is yes. The point is to give better advice that actually fills in the details of how to check for that this answer is actually correct, or at least to give the answer in more detail so that it can be checked. Okay? You'll notice that this is sort of a one-sided error definition, right? There's no way for the machine to make a mistake and accept something that should not be accepted, right? Because it always checks the advice, right? If you give it the wrong advice, it may reject something that should be accepted. Okay? So this is a one-sided error. And we call it non-deterministic because once we talk about this existence of advice that causes an accept, you can imagine the machine just guessing what that advice would be, right? So if you have a machine that has this supernatural power to guess, then it can guess the proper advice and it can proceed to accept acceptable strings only, and accept only acceptable strings, because if the string should be rejected, then there is no advice for it to guess. Okay? Now, I also introduced you to RP last time, right? So RP is the randomized case for this. It's really not that different from NP. It just says that instead of, the only difference is, so same as NP, except most advice inputs lead to an accept if the input is in the language, right? So in NP, there just has to be one advice string that causes the input to accept. RP says that on random advice, the probability that you accept an input in the language is at least 1/2. Okay, so instead of just having one advice string that works, you need at least half of the advice strings to work. Okay, this still in RP, you never accept a string that is not in the language. Okay. So we've got single, existence, we've got majority. What class might we have if I said you accept if all advice strings cause the algorithm or machine to accept? Just covering all the bases here. Right? No matter what advice string you give it, if the language is in the if the input is acceptable, then the machine accepts. Yes? Yeah. Yeah. Exactly. If every advice string works, then you can just have the machine generate the all zeros advice string, because that works. Right? So allowing all advice is polynomial time, allowing unique advice is NP, and RP is right in the middle with majority advice. Okay? Now, what if I change the fraction? What if I make it 1/4 or 3/4? How does that change the complexity class? Yes? Because? Exactly. Okay? So, the exact fraction is irrelevant. Obviously, if it's bigger than half, it's fine. If you have an algorithm which is some epsilon, then basically you just need to run your thing 1/epsilon times or so. And if it ever accepts, then you accept. Right? And this relies on the one-sided error characteristic, that no matter how often you run it, it's never going to accidentally accept. So if it ever accepts, you should accept for sure. And running it this many times gives you a decent chance that you will accept at least once. Okay? So notice that this works even if epsilon is, say, 1 over n squared, right? Because you're still running it only a polynomial number of times, so it's still a polynomial time algorithm. And we saw this case last time with min-cut. Okay? Any questions about that? All right, let's go a little farther because we have some more complexity classes. I introduced you already to ZPP, which is always correct, but runs in expected polynomial time. So the randomization does not change the answer, but it does change the time that it takes to get to the answer. Okay. And interesting fact, which we will prove, I think, next lecture, is that ZPP is actually the intersection of RP and co-RP. I told you about co-RP last time. This is where the one-sided error is in the opposite direction, where instead of having no false accepts, with co-RP you have no false rejects. Okay. And so what this is basically saying is that if you have one algorithm that is never fooled in one direction and another algorithm which is never fooled in the other direction, then you can get an algorithm which is never fooled. Okay? And until next lecture, I'll let you think about how to make that happen. Right? Also, if you have an algorithm with expected polynomial runtime, you can change it into an algorithm which has guaranteed polynomial runtime, right? But which only makes an error in one direction. And I'll let you think about that until next lecture as well. Okay. Yeah. Another complexity class, I don't think I got to this one last time, is what's called PP, probabilistic Oh, I should mention that the Z here stands for zero error. Okay, because it never makes a mistake. And the R stands for randomized. And you'll have to remember the difference between, the randomized polytime and probabilistic polynomial time. It's hard to imagine a semantic difference, but you just have to remember what they're used for. So in this one, you are again worst case polynomial time. And if your input is in the language, then the probability that you accept is greater than a half. Putting a greater here so that there's a clear distinction. If X is not in the language, then the probability you accept is less than a half. So this is kind of taking a stab at two-sided error, right? So you are more likely than not to give the right answer on any input. Yeah? Seems like a reasonable definition. Unfortunately, it turns out it's not a reasonable definition, not useful. Why do you suppose it's not useful? Yeah?
You could have like an algorithm that's like, if it's in the language, it succeeds with probability like 1/2 that's exponentially small.
Correct. Can you suggest such a language? Or such an algorithm?
Like, for example, like if you just consider like SAT,
Yes.
An algorithm like that would just be like, guess a solution and then check if it works.
Okay, but that only has an exponentially small chance of success, so that's not going to give you your bigger than half.
Like for your first like flip a coin, and then like if it's a bit more complicated, but it's
You're on the right track for sure. Yes. Go ahead. Yeah. Who just started speaking? I didn't.
Here's a statistic algorithm. Chain like for determining whether, say, like a number that like initially has a probability of like 1/2 of being prime, like is like.
Well, you can't talk about a number having a probability half of being prime because it's either prime or it's not.
Like,
right?
You can often there are like
But we are not doing expected input analysis. I will remind you of that again, right? We are not looking for an algorithm which is correct on half the inputs. We are looking for an algorithm that is always, that on every input is correct with probability of half, which is a much stricter requirement, okay? But on the track of what was said over there, imagine that you sort of do something stupid, try to guess a SAT answer, like pick a random satisfying assignment, right? If that doesn't work, then you flip a coin and say yes or no. Okay, so if you're lucky enough to guess the satisfying assignment, then you accept. Otherwise, you have a 50-50 chance of accepting. So your chance of accepting is slightly bigger than half. And if you bias the coin a little bit, you can make the chance of rejecting if it's not satisfiable also slightly bigger than a half. So essentially, what we've just shown is that NP is a smaller complexity class than probabilistic polynomial time. Okay, so PP is a super powerful complexity class and not something that we're going to be able to work with in practice. Okay, so in order to correct for this, we have BPP, which is bounded error PP, where instead of this half-half, we use 3/4 and 1/4. We push the errors away from each other. Okay. And again, right, so this is sort of mirroring PP except for changing the parameters. And again, the exact numbers don't matter. Okay, if your error bounds are like, you know, whatchamacallit, 6/10 and 4/10, or 51/100 and 49/100, it's fine. Why is it fine to have different numbers? Yes? So as long as there is a gap between these two numbers, they can be anything. Okay, it would actually be fine if you used 1/4 and 1/8. Actually, they don't even have to be on opposite sides of 1/2. But there does have to be a gap between them for the reason that I just told up here. That if there's a vanishingly small gap, if we're just using strict inequalities but have the same number, then you can cheat by taking a sort of a Hail Mary approach, like something that has a very tiny chance of success is enough to create that gap, but is not enough to be any kind of useful algorithm in practice. Okay? So for practical purposes, you need an actual gap. As with ZPP, it can actually be a polynomially small gap, but it has to be a substantial gap. What if it's different numbers? How do you get back to this 1/4, 3/4 gap in order to say that it's the same complexity class? Yes? Yes. So you run the algorithm many times. It's not quite as simple as just look for one except, right? But if you think about the law of large numbers, right? If you run the algorithm for many times, the number of successes is going to converge to the appropriate number, depending on whether it's an acceptable or a rejectable input. And we will formalize that accounting when we study tail bounds in a few lectures. Okay. So BPP is an actual, interesting, meaningful complexity class. There are many BPP algorithms, and you can actually implement them. There are all sorts of, so I will say, first of all, that we know the easy thing Whoops. And I also just mentioned that ZPP equals RP intersect co-RP. So we have some understanding of these complexity classes. But we also have plenty of open questions. We don't know if RP is equal to co-RP. We don't know if we can flip the direction of acceptance, right? This one is obvious. This one only takes brief thought. This one actually takes a proof, which we'll do later on. We really don't know about this one. And this is equivalent to asking whether RP is equal to ZPP. We don't know if you can always transform a Las Vegas algorithm in, sorry, we know in one direction. But we don't know if you can transform an RP algorithm into a ZPP algorithm in general. We also don't know, and this is a little bit embarrassing, whether BPP is contained in NP. Okay. Because NP is one of these one-sided error classes, and BPP has error on both sides, it seems conceivable, because BPP is sort of knows more about the distribution of witness values than NP does. And so maybe there's some weird problem that you can solve by sampling that you can't solve by guessing. Okay? Don't know. Okay? All right. Let me show you another kind of bizarre result from the perspective of complexity theory. For a complexity theorist, you can argue that randomization is pointless, that it gains you nothing at all. I'm going to introduce you to Adelman's theorem. Which says that in a certain way, RP is actually the same as P. But I will have to formalize what I mean by that certain way. Okay? So the question this is asking is whether randomness helps. And in practice, we know for sure yes. According to Adelman's theorem, well, in one model, no. In another model, maybe, but we don't actually know yet. So I'm going to give another representation of randomized algorithms. So let's consider an RP algorithm for inputs of a given size. Okay. So there's a finite number of those inputs. The definition of RP says that for each, if X is in the language, then half of the possible advice strings verify or demonstrate that the input is in fact in the language, right? The inputs that are not in the language cannot be accepted by this RP algorithm. I'm not even going to think about them. I'm just going to think about the fact that we need to somehow figure out how to verify all of the strings that should be accepted. Okay? So what I'm going to do is I'm going to make a matrix. In the columns of this matrix, I'm going to write down all acceptable inputs, all the X's that are in the language. Okay, so I might have 0, 1, 1, 0, and 1, 0, 0, 1, and 1, 1, 1, 1, and so forth. Just a whole bunch of inputs, and I'm going to think of them as strings, that should be accepted. Okay. In the rows, I'm going to write down all possible seeds. Okay, so we have zeros, and this is literally all possible seeds. So all of the bit strings that exist. Okay? And now I'm going to put a 1 if a particular seed verifies that a particular input should be accepted, and a 0 if that seed doesn't work. Okay. And so this matrix is going to get filled up with 1s and 0s in God knows what pattern. Yes? This is, of course, a very large matrix, right? Because it's exponential by exponential, but we don't care because it's only a thought experiment. Now, what I told you is that this is an RP algorithm. So from the perspective of this matrix, what does that tell us? Yes? Exactly. Every column, sorry, is it row? Every column is at least half 1s. Right? Everybody agrees? Okay, so here we have the one moment of deep insight in this proof. If every column is at least half 1s, that means that the matrix is at least half 1s. Right? Just counting up over the different columns. Yeah? But what that means is that some row is at least half 1s. Right? What does it mean that some row is at least half 1s if we translate that back to advice strings and polynomial time algorithms and such? Right? What does a row correspond to, and what does it mean that it's half 1s? Yes? Exactly. Some advice verifies half the inputs. Somewhere there is a good advisor. You just need to find them, right? Okay, why don't I take that advice and consider those inputs solved. I'm going to throw them away. Okay, I am now left with the unsolved inputs. Okay. The unsolved inputs remain in the matrix. What should I do now? Yes? Exactly, right? These unsolved problems, there's still an RP algorithm, right? Which is correct on half of the advice strings, which tells me that the remaining unsolved matrix is still at least half 1s, which means that in the remaining unsolved matrix, there is a particular piece of advice that solves half of the unsolved problems, right? So I can recurse or repeat, right? I can resolve half the unsolved inputs each time with one more advice string. Yes? So if I start with input size n, that means that I have at most 2 to the n inputs. Yes? Which means that after n rounds, I have less than 1, i.e. 0, unsolved inputs. Right? So what does this give me? Well, this tells me that if I just trying these n advice strings will properly resolve all inputs. Yes? So I started with a polynomial time algorithm. That's the definition of RP. And now I have an algorithm which involves running that algorithm n times that will solve every possible input. Okay? And that, of course, is still polynomial. I've only slowed down by a factor of n. Okay? This algorithm, however, is deterministic, right? I specify the n inputs, run on those, done. So, in a sense, I have demonstrated that any randomized algorithm can be turned into a deterministic algorithm. So why am I teaching this class? Yes?
Like the device may not be easy to find.
Exactly. What we've just shown is an existence proof, right? This advice exists, right? But I didn't tell you how to find it, and in fact, we don't know how to find it. Okay? And so in the language of complexity theory, what we have shown is that RP is contained in what's called P/poly. P/poly is a complexity class where when you're going to be running on inputs of size n, you are magically given a polynomial amount of special advice that will help you solve problems of size n. Now, is this just NP? Yeah? Exactly. So this advice is fixed by n, but it doesn't matter what input you get, right? This is universal advice that works for all inputs of size n. Okay? But it is still magical advice that has to come from some super intelligent AI source, right? So we can say that P/poly is contained in NP and contains P, right? Because NP is allowed to give different advice for each input. Yes?
But I think that's false.
Oh, it is?
P/poly, you could like decide, for example, like if you encode the holding problem in unary, then like the advice can just be like the answer like that equivalent. So like P/poly can just disable languages.
I don't think that you could fit the halting problem into a polynomial amount of advice.
Like unary, like only once.
Encode it in unary only once. Okay, let me take that discussion offline because that probably is going to take a while. So I will hold off on making this assertion until I have that discussion. But the point is that P/poly is still a kind of a non-deterministic complexity class. Another way to think about it is that it's really a different algorithm for each n. Right? So for each n, you take your RP algorithm, you attach the advice, and that's a different algorithm. So this is what is known as a non-uniform complexity class. It isn't one algorithm that works for all input sizes, but instead is a family of algorithms. And the point is that the family has to have a runtime that is polynomial, right? So as you look at the running time for each n, you have a function that is growing as a polynomial in n, but you can have a different algorithm at each size, okay? And of course, I think this sort of shows you that this is not a useful practical consideration, right? You're not going to implement, you're not going to use Adelman's reduction to get a deterministic algorithm out of a randomized one. Except if you go a little bit deeper, what we showed here is, I mean, we argued that just one advice string is going to cover half of the inputs. But if you analyze it a little bit more carefully, what we're really saying is that a random advice string will tend to solve about half the inputs on average. And so you can actually sort of construct an Adelman's algorithm by randomly choosing n advice strings, or some polynomial number of advice strings. But you can't check whether they work. So even that is not something that you can think about doing in practice. Okay, so this was just sort of a fun exercise in complexity theory. Let me start bringing us back to algorithms now. We're now going to look at a particular problem which sort of exists just to help us understand more about this difference between P, RP, and NP, but it's actually a pretty natural problem, which is game tree evaluation. Okay, so the idea here is that I'm going to think about a game between two players, and to keep it simple, each player will have exactly 2 moves at each turn of when it's their turn in the game. Also, to keep it simple, the length of the game is going to be exactly h. Okay, that is, and we can represent this, right? So 2 players, 2 possible moves per play, a game length of h, which means h over 2 moves per player, because they're going to be taking turns. And I'm also going to say that the game always ends in a win or a loss without any draws. Okay. Now, we can represent this as a game tree. Right? We start at the beginning of the game with player 1 moving. And they have a choice of 2 moves, which gives me 2 children. And at the point of those 2 children, player 2 moves, right? Player 2 also has choice of 2 movements in each state of the game. Now player 1 moves again. Now player 2 moves again. And depending on and perhaps now the game ends. And at this point, there are some wins and losses for the different players. And I'm going to say this from the since I've got player 1 at the root, I'm going to represent the wins and the losses from at the leaves, in this case, from the perspective of the player who would be moving. So player 1 in this case. Okay. So I can write out a game like this, a game tree, that describes the game. And this is a very simplistic game tree, but of course, these game trees show up all the time when you're building your chess solver or your checkers solver or whatever. It's just that they have a larger branching factor and a depth that's greater than 4. Okay? You know, tic-tac-toe will have an initial branching factor of 9, and then those children will have a factor of 8, and so forth. So the question is, if you are looking at a game tree like this, who wins? If both players play perfectly. And that is sort of not immediately obvious, but if both players play optimally, one of them can force a win. Okay? Either player 1 can force a win or player 2 can force a win. And that's not completely obvious and can help us build some intuition. So who would like to prove that one of the two players can force a win on any game tree? Yes? Great. So we need to focus on this notion of all possible responses, right? So in what circumstances does player 1 win? Well, player 1 wins if they have a move that will force player 2 to lose. So under what circumstances is player 2 going to lose? Well, player 2 is going to lose if they have no move that will let them win, right? So if we want to look at this recursively, we can say that the root wins if the root has a move such, or this actually applies to any node of the tree, right? A node wins if it has a move such that the child loses. And conversely, a node loses if both moves lead to a child win. And if you think about it, this exhausts the cases, right? Either you have a winning move or you don't have a winning move. If you have a winning move, you win. If you don't have a winning move, you lose. Is that clear? So now that we have this definition, it should be clear that you can recursively analyze this game tree in order to decide whether there's a win or a loss. And I mean, sorry, there's different notions of recursion, right? I can say that to recursively solve the problem for P1 at the root, to solve the problem at the root, I need to recurse on the two children and find out whether these are wins or losses. And I'm always talking from the perspective of the player who's going to move, okay? So if these are both losses for P2, then this is a win for P1. If, on the other hand, one of these is a win, if one of these is a loss for P2, then P1 can go there and make it a win for P1 from the root. If both of these are losses for P1, then P1 has no move that will let them win, and therefore P1 has a loss. So you can evaluate this game tree recursively and deterministically in time, which satisfies a very simple recurrence. So we have a nice, simple polynomial time algorithm, which just is based on evaluating both of the children, which means that T of H is equal to 2 T of H minus 1. Yes? And I'm going to measure just in terms of number of leaves that you have to look at. I'm not going to worry about the actual computation, but just how much of the data you actually examine. Okay? Which of course means that the runtime is 2 to the h, and I'm going to write this as n so that I don't have to have too many exponents flying around. Okay? So this is a simple deterministic polynomial time algorithm, or polynomial in n, right? In this, and notice that n is the size of the tree, right? So it is reasonable for me to call this polynomial in a polynomial time algorithm because we're talking about the input being the entire tree. right? Obviously, if you're talking about chess, this is not how you provide input to the algorithm, okay? This is an example of an extensive form where you've kind of written out all of the possible strategies that players could choose, okay? Notice, though, that actually, if I wanted to sort of describe a strategy for the players, I'd kind of have to explain which move they would take at any position, at any tree, at any node in this tree, which means that describing a strategy also takes polynomial space. And the number of strategies is exponential in the size of the tree. So it's actually doubly exponential in the depth of the tree. So finding an optimal strategy is not a trivial thing. You're exploring an exponential size space. Okay. But let me ask a question. Is this the best possible deterministic algorithm? Can you give me a lower bound? Can you show me that a deterministic algorithm actually has to, like, this algorithm is looking at all the leaves, right? It's recursively solving both children. Can you convince me and all your classmates that this is necessary? Yes. Yeah, I think you're seeing it in your head because there's a sort of a natural class of algorithms, right? Where you check one child and then you check the other child, right? If you think about this class of algorithms where first you check one possibility and then you check the other, then you can make a pretty straightforward argument that there's always a bad outcome, okay? But is it obvious that all such algorithms, that this is the only kind of interesting algorithm? Might it make sense for you in evaluating this game tree to kind of explore partway down one subtree and then say, this is not looking so good, and switch to exploring down the other subtree so that you don't do one subtree at a time? And the answer is no. You can argue by induction that it really makes sense that you really should evaluate one tree entirely and then evaluate the other tree. And you argue that actually by making an even stronger statement, okay? The inductive statement is that the adversary can always give leaf answers such that the correct answer is unknown until you see the final leaf. Okay. Until you have looked at every single leaf, the answer could go either way. All right. The proof is not very difficult. What you do is, since you have this induction, I'm going to you can see that this algorithm is driven entirely by eventually getting to leaves and finding out whether the leaf is a win or a loss, right? Everything else is just bookkeeping. So as the algorithm makes its inquiries about different leaves, I'm going to keep both children of the root ambiguous, relying on the inductive statement, on the inductive hypothesis, until you query the last leaf of one child. Okay. what are you going to do as the adversary when I am finally forced to ask about the last leaf of one of the children? Yes? Other way around. If the child loses, that's good for me, and therefore I should move to that child, right? I'm going to flip it, right? I'm going to make that first child a win for that child. And that means that all of the work I did looking at that subtree was wasted, because I do not want to use that subtree. So at this point, I have to resolve the other subtree. Which, by induction, is going to require me to do a full analysis of the other subtree. So at this point, I've fully evaluated both subtrees, and that proves my inductive step. Is that clear to everybody? If it's not, ask a question. Okay, so essentially what we've now proven is that 2 to the h equals n is optimal for polynomial time algorithms. Oh, I didn't need to do that. All right, let's think about some other complexity classes. To build some intuition, let's talk about NP. Okay. So with NP, we are allowed to advise the algorithm on which leaves to look at. And if you think about it, what this means is we no longer need to figure out whether the tree is a win or a lose. We just need to construct a proof that this tree is a win or a lose. Okay? It is sufficient to non-deterministically build a proof of the win-loss outcomes for a given tree. So what do I need to do in order to prove that this tree is a win or a loss? Let's look at them separately, okay? So to prove my tree is a loss, what do I have to do? And let's think recursively again. Yes? What was that? Exactly. I have to prove that both children, wait, no. To prove that this is a loss for me, yes, I have to prove that both children win. Right? Which is exactly what we did with the deterministic algorithm. But what do I need to do to prove that the tree is a win? Yes? Exactly. Prove some child is a loss. Okay? And the point is, I can assume that I'm given the proof, right? That's my non-deterministic advice. And all I have to do is look at the leaves that it tells me to look at in order to construct this proof. Okay? So we can now state this in terms of a runtime, right? So if I want to prove that I have a given win, that I have a losing tree at height h, I need to construct proofs that both children are winners. Yes? On the other hand, to prove that a tree is a win, I only need to look at the right child, the correct child, and prove that it's a loss. Yes? So if I put these together, I can see that losing at H, or sorry, let's do it with wins. Winning at H costs me losing at H minus 1, which costs me 2 winning at H minus 2, right? And so there we had, you know, winning or losing cost me twice at H minus 1, but now it's H minus 2. So we have a better recurrence now. Instead of 2 to the H, we get 2 to the H over 2, which is root n, as the running time for a non-deterministic polynomial algorithm, or alternatively for a proof checker as compared to a proof constructor. It takes the square root of the running time. Is that clear? Any questions? Okay, yes, go ahead. That a tree is what? Oh, that's the thing that we argued first. Right? Essentially, it's that the proof of that simpler statement is hiding in the proof of this more extensive statement, right? Essentially that, or sorry, it's actually up here, right? You win if one of your children loses. You lose if both of your children win. That's exhaustive cases. So one of those two things has to happen. Well, to claim that there is either a win or a loss, you don't need to search the tree, right? We just need to consider these two possibilities, that either one of your children wins or they don't. And that determines whether you win or not, okay? This is where we looked at how much you needed to look at the tree in order to decide what the outcome was, okay? All right, so now we've got P and we've got NP, and over there I argued that RP was between P and NP, and now I'm going to show you how RP is between P and NP, but let's take our 2-minute break first so that you can recharge. Yes?
I filled out the form, but I can't log in.
When did you fill out the form?
Last Wednesday.
Last Wednesday. Okay, did you try logging in with both your email and your username, which is the thing before the @ sign? Okay, I have a 15-minute meeting at 4 o'clock, but if you can join me in my office at 4:15, we can try and debug what's going on. You will have to reset the password in order, like that's the point. You don't, if you've created your account, you don't have a password you can use yet, and so you should go through the password reset process, and then you should be able to log in. So try that first. Sure. No, it is true that the unary halting problem is undecidable, but it is the halting problem is decidable for fixed size of machine.
Wait.
Because there's only a finite number of machines, so you can just write down all the answers to the halting problem.
Yeah, so like that is the unary halting problem is in P poly,
Yes.
which means that P poly contains undecidable languages.
Wait, oh, I see what you're saying. Yeah, I have to wrestle with the definitions. The unary halting problem is in P/poly. Yes, of course it is, because it's non-uniform, because you can write down the answers. Yeah, I think you're right. I think you're right. Yeah, once you get non-uniform, you can do crazy powerful things. That's kind of the point.
Like circuit size, like non-uniform circuits need not be decidable because like the circuits themselves can be like decided by some like undecidable function.
Oh, right. P slash poly has stronger.
Yeah, we have to think about that some more before I start making any claims.
Oh, because like you can't verify that. You cannot verify that like, the advice is actually.
All right, let's resume with the RP question. Okay? Or rather, the ZPP question. Okay, so we're going to focus on an algorithm that always gives the right answer, but the question is how quickly can we give that right answer, and we're going to use randomization in our choices to try to give that answer more quickly. Okay, so given these two algorithms that we've sketched out, right, the deterministic one that is forced by an adversary to examine both of the children, right, and this non-deterministic algorithm which cleverly chooses the proper child to evaluate so that it doesn't have to evaluate both of them. But unfortunately that relies on non-determinism, which we can't implement. We can, however, implement randomness. So do we have any thoughts about how we might use randomization to get around the lower bound of the deterministic algorithm? Yes? Exactly. The most natural randomized algorithm in the world is evaluate a random child and then evaluate the second if necessary. And what is it going to make? What's going to make it necessary to evaluate the second child? Yeah?
If the child you just evaluated is a win.
Right. Okay, so let's work through our analysis of this. Now we're randomizing, so everything gets notationally a little bit messier, right? Because we have random variables everywhere, right? So what I can talk about is W of t, which is a random variable representing the time it takes to prove that t is a win, which is only defined if t is a win. Okay. And similarly for L of t, which is a random variable which represents the time it takes to verify to find that t is a loss, and is only defined for trees that are losses. Okay. And again, these are random variables which are randomizing over the random choices of the algorithm. This is not randomizing over game trees, right? We are considering the worst case t and imagining the randomness happening for this worst case t. Okay. Now, I don't know what this worst case t is. I will later, but I don't know now. But I can define W of h to be the max over height h trees of the expectation of W of t, right? And similarly for losing trees. Okay. Agreed? And the question is, can I define sorry, go ahead, question? No, that's exactly what I just said. We are not randomizing over t, right? What we are saying here is consider all possible t's. For each t, if it's a winning t, there is a w of t random variable, right? And now I can compute the expectation of that random variable w of t. And that is a number associated with that particular tree. Now I consider the worst of those expectations over all possible trees. Okay, we are never, with few exceptions, we are never going to randomize over inputs in this class. Okay? Because you can't do it in the real world. Right? You have to take the bad input that your advisor gave you. You don't get to pick a random input. I mean, that is what we do when we're testing programs, but that's why we still have bugs in the real world. Okay, so can we figure out a recurrence that captures what's going on with these expectations? Let's start with the easy one. Okay, so if I'm losing, what do I need to check? How do I find out that I'm losing? Yeah? Exactly. So what I can say here is that the losing variable for t is equal to the winning variable for the left subtree plus the winning variable for the right subtree. Yes? So what does that tell me about L of h? Yes, in the back.
That it is 2 times like w of h minus 1.
Exactly.
Plus O of 1.
Well, remember, we're just counting leaves here. So there is no O of 1. Right? So L of h is at most, right? So the point is that this WT left is less than W of h minus 1 by the definition, or sorry, let me put some expectations. Sorry. I can now put expectations around all of this, right? And if I take the expectation on the left, I get the definition of L of h, right? If I take the expectation on the right, I have linearity of expectation. So I can pull apart these two, and I have a W of h minus 1 over here and a W of h minus 1 over here, which upper bound the expectations for these two trees. And so that means I have this bound. Yes. And again, I want to emphasize this. This works because I'm using linearity of expectation, right? That this algorithm is running two sub-algorithms and adding their times. Okay? Yes?
I think we can say that LH is equal to WH minus 1 because LH is defined to be like the worst case.
I don't want to stop and think about whether the worst case height h tree involves two worst case height h minus 1 trees, but you're probably right. Okay? But the point is we're only upper bounding, so it doesn't matter. Okay? This is the harder case. Okay? What am I going to be doing? What's the situation going to be if I am trying to prove that my tree is a winner? What does it mean for my tree to be a winner? What's the definition? Yes? One of the children is a loser. Okay? So that suggests, right, if I'm putting my WT over here, that there's going to be a W of T something on the other side, right? But what else is going on? Yes?
Well, since you're picking like randomly, you don't know whether like pick the first one and it was like a loser, or like maybe like pick the first one and like randomly.
Right. So this is where things get complicated, is that our first choice might be the one that is a winner, right? Sorry, it's loser of T sum, right? The first choice might be the child that loses, right? And I know I'm going to have to evaluate that child, right? I'm going to evaluate some losing child. The problem is there's another child that I might pick first, right? So there's also going to be this W or L, right? Of the other tree. I'm sure you love my mathematical notation here, but hopefully it's clear what I'm saying, right? So one possibility is that I just pick the right tree first, and it is a loser, and I'm done. The other possibility is that I pick the other tree, and it is a winner, and I evaluate it, and I've just wasted time doing that winner evaluation, and then I have to go back and evaluate that the other tree is a loser. Okay? So let's try to write that out a little bit more formally. So essentially, if I'm trying to figure out W of t, there's sort of a 50-50 chance of different outcomes, right? One of the outcomes is that good things happen. On some tree. But the other possibility is that I do compute that loss, but there also was this tree that was a win, or maybe a loss. But if we think about it, evaluating a winning tree takes less work than evaluating a losing tree, because with a winning tree, you only need to evaluate the losing child, right? And so the worst case here is going to be where yes, go ahead.
I was wondering why we're like adding the L twice, because like we would only have to do 2 checks if the first check was a win. So we would like never have to add 2 losses, right? If we just see a loss, we're done.
Exactly. That's exactly the point, right? So this goes away, right? The point is that half of the time, right, we're going to, if we have a bad situation where there's one win and one loss, then half the time we will have to evaluate the win, and then we will evaluate the loss. The other half of the time, we will just evaluate the loss. If we're not in an adversarial situation where both the children are losses, then whichever one we evaluate first, we're fine, right? We find the loss. So in a good case, we will always be spending this L. In a bad case, we have a 50-50 chance of spending an L plus a W. Does that make sense? Right? So if both of the children lose, we pay L of h minus 1. Right? If one wins, then half of the time we're going to pay L of h minus 1, and half of the time we're going to pay W of h minus 1 plus L of h minus 1. Yes? And I'm using the same linearity of expectation argument here, right? That actually we have these 2 random variables around the trees, but since we're upper bounding, we can use the maximum expectation over all trees in our upper bound. Okay? So we put this together. We find out that W of h is at most. We have the L of h minus 1 in both cases, right? But half of the time, we are also going to spend a W of H minus 1. Yeah? So yeah. And notice that, as I said, if they're both losers, you're only paying L of H minus 1, and this term isn't here. So this is the worst case. This is the upper bound, right? So an easy analysis of this would just say that L of H minus 1 is less than W of H minus 1. So this is at most 3/2. Sorry, L of H minus 1 is less than W of H minus 2. So a simple analysis of this would just say that W of H is less than 3/2 of L of H minus 1, which makes it less than 3 W of H minus 2. Okay, which would mean that L of H is less than or equal to 3 to the H over 2. And isn't that nice that sort of deterministically it's 2 to the H, it's 2 to the 2H over 2. Randomly it's 2 to the H over 2, non-deterministically it's 2 to the H over 2, and randomly it's in the middle. But we can do a little bit better by actually solving the recurrence. If we solve the characteristic equation, the characteristics polynomial here, what it tells us is that we write out W of H as being less than 2W of H minus 2. That just comes from the plugging in for L of H minus 1, plus 1/2 W of H minus 1, which means that our characteristic equation is that x squared minus x over 2 plus 2 is equal to 0. And that has a root at, that has a solution to the recurrence is alpha to the h, or order alpha to the h, where alpha is just the solution to this characteristic equation, 1/4 of 1 plus the square root of 33. Don't ask me why. And that tells me that W of H is, that W of N, right? Remember, N is equal to 2 to the H, is about N to the 0.753. So it's some weird irrational, but the point is that it's about N to the 3/4, right? So again, deterministic is N, non-deterministic is square root of N, randomized is squarely in the middle at N to the 3/4. Yes, questions?
Two questions. So for the easy analysis, you are assuming something like L of H is less than W of H?
Yes.
Okay, and then for the characteristic polynomial thing, the way that works is that you assume that the solution has the form
Correct.
alpha to the H.
Yes.
Okay.
That is correct. Yeah. So I'm assuming that you've all seen the use of characteristic polynomials to solve linear recurrences. If you haven't, don't bother, because this is the only time we're going to use this in the class. But it's a cute trick, okay, for solving linear recurrences. Question? No. I will say this again, but I mean, I will repeat this over and over again because it is fundamental in this class. Our randomization is never over the inputs. Our randomization is always over the random choices that are made when we are running the algorithm, okay? And so we define these random variables that are, like, once you fix a tree, you get a random variable. But we're now analyzing the distribution of running times for a given tree. Once we have a distribution of running times for a given tree, we can talk about the expected running time for that tree. Yes? And we are now, here what we are analyzing with W of H is the worst expected running time. And the way that we're doing that is by saying that to analyze a tree, you analyze the two children. And we can therefore bound the cost of analyzing the two children not as randomizing over the trees, but just using the worst case running time for evaluating the children in expectation over the random choices of the algorithm. Okay? So I think that this gives you a very concrete picture of how randomization sort of nestles in between deterministic and non-deterministic algorithms. It gives you a kind of non-determinism that you can actually execute in practice by making random choices. Now, there remains an interesting question here. We argued that our deterministic algorithm was optimal. It's pretty easy to demonstrate that the non-deterministic algorithm is optimal among non-deterministic algorithms. But did we actually find the optimal randomized algorithm? How do we prove that this randomized algorithm is optimal? Okay. And what that basically boils down to is, how do we prove a lower bound, right? We know how to prove deterministic lower bounds by giving a bad input. But how do we prove a lower bound on the expected runtime of a randomized algorithm? Now, those of you who took advanced algorithms last year have a little leg up here, and you'll get 5 minutes of recap at the beginning of next lecture as I explain this very interesting technique for proving lower bounds on the run.